Last video we talked about pressure variation while fluid is at rest, and then we derived specific weight formula. Now we're gonna derive application in incompressible fluid using what we have so-called understand. Okay, so this equation is trying to find the pressure at this range. Okay, because you want to know the pressure at this range. And then, however, this requires a multi-level type of thing. Okay, anyway, so we think that this free surface, okay, at pressure is P equals to P naught, which is at atmospheric pressure, which is air itself lah. Okay, and then once you are going in depth, there will be um, rho GH comes in, where H is the height itself, height of the depth lah. Okay, so if you remember, pressure is equals to rho GH, right? And we take that if you are going downwards, the downwards is actually minus. Okay, so minus rho G, while H is a small change in the Z. Okay, and then we integrate the changes. So the changes in Z, if you know, because typically we will derive pressure head itself. Okay, so you get what I mean. So the change in height will actually cause a change in the pressure because the density and the gravity will assume constant in compressible fluid, and therefore if you were to take an integration, okay, from z1 to z2, okay, z1 is at this is this height, I mean this depth, and then z2 is this one. So you're trying to find h, right? So typically it's z2 minus z1, you get h. So this is what it means. So you're trying to integrate from z1 to z2, z1 position to whatever. So you're just trying to formulate an equation lah. Okay. So from maybe I should think a while. Okay, after I think for a very long time. Okay, you see the time now, 9:16 already. It is the z2 and z1, and p2 and p1 is just a symbol or a notation to describe the position. It doesn't contain any quantity, I would say. Okay, for z1 and z2, z1 and z2 is just a position to use to describe the difference. Okay, which is, although it may seem very easy, but if you try to explain it, it's, I don't know, for me it's a little, but now I understand. So the reason is from z1 to z2 is from this position, z1 to z2, and this z1 and z2 is from datum point at y, I mean at the seabed itself, I would say. So from z1 to z2 means that there is the interval from this position to this position. So this is why it's minus. And then because we are trying to find the differences in the quantity in H itself, the quantity of pressure in H, I was like, wow, you can actually use the difference, you can actually calculate the difference using integration in such manner, which is, I don't know, maybe yeah, anyway. Okay, so minus rho g, z2 minus z1 is actually h, the difference in that. So you can say that p2 minus p1 equals to minus rho g h. The h that is the difference between certain point to a certain point. Okay, just to repeat again, h is the difference between one point to another point. It's not the depths. Okay, it's not the full depth of the seabed itself. And then okay, I'm not trying to complicate things, but yeah, it's just h. It's the depth. It's the depth of the position of wherever your item is from a certain datum point. Yeah, whatever. So if they're trying to call you to derive this equation, it is simple, but it is intuitionally mind-blowing. Okay, you have to set your datum point, and then you set the positions, and then you say that you integrate from this point to this point, so that Z2 minus Z1, you have the potential, you have the difference in the pressure. It's a very simple formula, so eventually you get this, and then you rearrange, you just bring P2 forward, you get minus P1 equals to minus P2 minus rho GH. So everything becomes the same convention, because minus P1 is here, then P2 go over here is minus P2 so everything is minus. So you can also say that it's plus. So P1 equals to P2 plus rho GH. Okay, so rho G, as we derived earlier, is the specific weight. Therefore, it's this. And then yeah, this is rewritten. And then we can also describe the definition of pressure head as this. So it's just you bring this over, and then you divide it by the rho G, okay, which is the specific gravity, and you'll get your pressure head. So this is the relationship. So I just want to say that the technique in using this, you require a datum and the position from somewhere to somewhere, and then you integrate. From here to here. Wow. Anyway, so application in a compressible fluid. Okay. Oh yeah, one thing for this is that this is linear. Okay, incompressible is linear. Why is it linear? It's because as you can see, the final equation is in this form. What is this form? Y is equals to mx plus c, the change in height. Okay, so it's a linearized form. And then for compressible fluid is a non-linear, which takes on this exponential term. Okay, so for compressible, it is an ideal gas, okay, or ideal fluid. So we will use PV equals to MRT, okay, if you remember. So you rearrange, you get rho equals to pressure over RT, okay. By how do you rearrange? Okay, volume you bring over here, RT you bring down, okay. So mass over volume is equals to density and equals to P over RT, okay. And then you use this equation, and then you sub that into 7, which is this equation. So you are still gonna go back to a specific weight. This is your specific weight. The change in pressure again along the change in the depth itself. So you use this and this, and then sub in into your, because you know that density is equals, can be rewritten as P over RT. Okay. So also take note that this is when the fluid is at rest. So this is why we can also use this formula in. Okay. So you just substituting density into the equation. Okay, which is also gamma lah. Okay, in your specific weight equation, you get this G. Okay, rho G, and then now let me see. Hold on a while. Okay, so you rearrange, you bring the P downwards, you bring the dz upwards. Okay, so dz is over here, and gr and rtr didn't change, dp didn't change, and the purpose of this in this arrangement is to ensure that this is a separable equation, so that the p is with the p, and then you can take g and over rt as a constant, and you can integrate dz itself. Okay. So because this is actually a differential equation already, a first order. Okay, so you can actually solve using a simple separable equation. And then you solve for your thing using the same approach of from Z1 to Z2, but in this case it's compressible fluid. However, this diagram can be applicable, and therefore sorry, my throat is getting sore. I talked the whole day already. And you eventually get Z2, because from Z1 to Z2, if you remember. So Okay, give me a minute. I go and drink water. And yeah, and you integrate. Okay, integrating wherever. Okay, p. Okay, it's 1 over p dp, right? So it's a ln p. From ln p2 minus ln p1 is actually p2 over p1. That's why it's ln p2 over p1. Okay, this is the logarithm rule. And then it's the same thing, z2 minus z1. And then what are the difference between this formula? Oh, between this formula and this formula, you give me a while. Reason why it actually changed sign, okay, z2 minus z1 changed to z1 minus z2, and p2 over p1 changed to p1 over p2, is to ensure that the final result is in terms of positive, okay, because p0 is actually atmospheric pressure. When you exponential it, okay, you're actually increasing the amount of atmospheric pressure. So let's say atmospheric pressure is 101 kPa. So exponential it maybe with certain height, your pressure will increase because with a depth you increase pressure, right? So therefore, in this manner you can also calculate, but rather than they want it to be positive, so it is easier. I don't know. Yeah, it's just a notation for them to calculate in an easy way. So it's just a matter of rearranging. Okay, it's rearranging the things only. But the reason why it changes, okay, anyway, it's the position only ma. So never mind. So if we change the position z2 to z1 position, then z2 to z1 position, we are changing p2 position to p1 position. I hope you get what I mean. Because the position, as I say, the notation here are all positions. Okay, z1 position and z2 position, and then it is trying to do these things. Once you set this thing, um, you can actually solve for your you can actually make a p. You just multiply exponential. You just solve for this line. Eventually you know that p1 is equals to p2 e minus grt. And then since z1 is definitely lower than z2, as you know, so z1 minus z2 will be negative, right? Because as you know, z1, the amount of distance compared to z2 is so much. So therefore, this whole thing becomes positive, and we can say that this is h. And this z2 is equals to the h, as I say earlier, as they say earlier lah. Okay. So it's the height lah. Okay, it's the depth of the water. And then this is it. I think I'm not going to continue any videos. My throat is kind of getting terrible. But before I end this video, I'll try to summarize what are the key terms. Is that the magic behind the z2 and the z1. Okay, you have to really set a datum first, and then set your z1 and your z2 in order to have this equation from z1 to z2. Then you can solve. Then you can know that if you were to integrate, it will become z2 minus z1, which is the height. Which you also can use to determine the pressure, the difference in pressure, okay, in this sector. And then for what we have told earlier, okay, we are dealing with incompressible and compressible. So for incompressible fluid is linear, okay, it goes about the equation of rho1 equals to rho2 plus p2 equals to p1 equals to p2 plus rho h. And then for compressible fluid, which is non-linear, okay, non-linear is exponential. So we calculate pressure for compressible fluid using this. And then p0 itself is atmospheric. Just take note. So this is the equation you need to know, and this is the equation you need to know, and also this the pressure head. And then with this, I think I'll just end here. So you know that we already clear all these things. So for the next few videos, we talk about this too. Most things are about this, which is really I was okay. Anyway, so be prepared that this portion is a little complicated. So see you.